tables, and I'm going to give you some insight into quiz 9 and quiz 10. When it comes to the notion of truth tables and truth trees, which have to do with your quiz 9 and quiz 10 coming up, what these are validity tests. What that means is this. Think about it this way. Every single proof you've done so far this semester has been a valid argument. The proof has worked. But there are some times maybe when there's a proof in front of us and we don't know if it's going to work or not, and we don't know, is it an error on my part? Am I not able to solve it? Or does it actually work in spite of my inability to solve it? So that's how truth tables and truth trees work. Now I'm going to talk about truth tables first, and that's the subject matter of quiz 9, and then we're going to talk about truth trees, which are the subject matter of quiz 10. And actually the problems on quiz 9 and quiz 10 are going to be the same for both, just quiz 9 is going to be on truth tables, I'm doing it that way, and quiz 10 is going to be doing it the truth tree way. So you're going to have the same problems, and so that's going to help you, that's going to enable you to be able to figure out, like, hey, I got this on quiz 9, does it match up on quiz 10? And if you find yourself getting something different in the results, then you've messed up somewhere. So how does this work? Well, let's start with this. Let's start by doing the table method and looking at two simple arguments. Simple not in the sense of simple between simple and compound, but not too much going on. Let's take a look at the following two arguments. Okay. A arrow B, A, B, and then let's take a look at this one. A arrow B, B, A. Now, one of these arguments should look familiar to you. This right here. Hey, this is arrow out. We got an arrow. We got a left side match. Hey, you get B. This one, we got an arrow. We don't have a left side match. We don't have a right side contrary, so we can't do modus tollens. We know this one works. Does this one work? I can't think of a rule for this. Does it work or not? Now, the answer for this one, does it work, is yes. And the answer for this one is no, it doesn't. But this leads us to a problem. Like, I know this one works because I know the rule for it. Maybe this one works and I just don't know the rule for it. Is there a way for me to figure out, does it work or not, without me being able to do a proof? Yeah. Tables and trees. So let's start with the table method. And so truth tables are going to tell us, yeah, this one works and this one doesn't. Okay, let's start with truth table rules. And so these are all diagrams here. I'm going to explain these diagrams and then we're going to use them in a little bit. So first of all, let's explain them as diagrams, and then I want to show you how to use them. So I'm going to go through all of them here. So here's all the truth table rules. So first of all, table rules for not. And so what these table rules do is they show us how the connectives work in terms of their truth values. So what do I mean by that? Well, take a look. Let's start with the not one. So this is the table rule for negation. What it's telling you here is, hey, here's the two possible scenarios when you have A. Here's A. Here's squiggle A. Okay, so if A is true, then what do we know about squiggle A? It's not true. If A is false, then what do we know about squiggle A? It's true. Now, where I have truth and false here, T and F, in binary language and programming languages, and also if you studied to be an electrician, you will do the same stuff here, except instead of T's and F's, you will deal with ones and zeros. The stuff is the same here. These are actually logic gates, whether you're doing computer science or you're doing electronics. Same kind of stuff here. But that one's pretty obvious. This one's pretty obvious too. Think about this. Think about this is the AND rule. The AND rule says this. And think about it this way. What's the only time an AND statement works? If I say A and B, what's the only time an AND statement is true? Well, when both of them are true. If I say something like, let's say it's Tuesday and we have a test today. If I say it's Tuesday and we have a test today, the only way this statement, it's Tuesday and we have a test today, would be true is if the individual parts are true. So, hey, it's Tuesday, but it's actually not true that we have a test today. Well, then this statement is false. It's not Tuesday, but we have a test today. Well, then what I said was false. And then this one, they're both false. It's not Tuesday, and we don't have a test today. Well, then this statement would be false. So let me put it this way. The only time an and statement works is if both parts are true. Any other instance, it's going to be false. Okay? That's what you need to know here. For ors, and this makes sense here too. For ors, now we've got or here versus XOR. Remember, the way an inclusive disjunction works is as long as one part is true, maybe both, the disjunction works. The only time this disjunction does not work is if both parts are false. And that's what we see here. If both parts are false, this doesn't work. One part's true, it works. Another part is true, it works. Both parts are true, it works. So if I said something like, today is Tuesday, or we have a test today, both those things are true, we're good. It's Tuesday, but we don't have a test today, right? It works. It's not Tuesday, but we have a test today, and we actually do. That works. So as long as one part is true, we're good. The XOR, on the other hand, says, no, you got to pick one. Either only one can be true. So either the left one's true, then it's good. The right one's true, then it's good. If both are false, nope. If both are true, that can't happen. That's what makes an XOR different from an OR. So that's really the difference here. Otherwise, these two are the same. It's this top line. When all are true, inclusive OR works. When all are true, XOR does not work. Arrows and double arrows. So let me start with actually the double arrow here. The double arrow here is pretty straightforward. Double arrow works this way. One side's true. It's all or nothing. If all are true, the whole thing works. If all are false, the whole thing works. Any mixing and matching doesn't work. So here's what I mean by that. Here's what I mean by that. So let's say I said something like A stands for, it's triangle, B stands for it's got three sides. Well then, if it's triangle, it's got three sides. Yep, that works. If it's not a triangle, then it doesn't have three sides. That one works. But if I start mixing and matching, it doesn't work. It's a triangle, and it doesn't have three sides. Nope. It's not a triangle, but it does have three sides. Nope. That doesn't work. Okay? So that's what's going on here. And then let's look at the rule for arrows. When it comes to the table method. The table method says this. For arrows, and arrows, they sound a little bit confusing here. So, let me put it this way. Let's say, for example, that A stands for you clean your room, and B stands for I'll give you ice cream. In which one of these situations am I a liar or not? All right, you clean your room. If you clean your room, I give you ice cream. And you clean your room, I give you ice cream, then this statement is true. Okay? And let's say you clean, let me go down to these other ones here actually. You didn't clean your room. Can I still give you ice cream anyway? Yeah, just because I feel like it. That makes the statement true. You didn't clean your room, I didn't give you ice cream. That's right. But here's the only situation in which I'm a liar that results in a false implication. Hey, I told you if you cleaned your room, I'd give you ice cream. You cleaned your room? Nah, I'm not giving you ice cream. Well, then in this situation, I'm a liar. But in all the other situations, well, like even in this one, like, hey, you didn't clean your room? You know what? I feel like giving you ice cream anyway. The arrow is still true. So the only time an arrow doesn't work is when you have a true left and a false right. That necessary condition, then, is not necessary. Nope, that doesn't work. So these are the rules for tables. And so when we get into tables, I think we're going to apply the stuff here into tables to determine the validity of various arguments. So we're going to apply these now. So you don't need to commit these 6 things here to memory, but we're going to apply them to see if arguments are valid or not. So let's go back to that first example I had between those 2 different short arguments and apply these rules. I'm going to show you how to apply these rules and see what we get, what I'm trying to do. So let's deal first with this argument here on the left. Now this should be familiar to us. This is arrow out. So here's what I'm going to do. First of all, I'm going to write my constituent components. My letters here are A and B. So what I'm going to do here is I'm going to write out every possible truth combination that could happen between them, which there are 4. And I'll post a PDF that shows the way to get to do this in a systematic way. But basically, here's how it goes. Here's how I do it. There are 4 possible truth combinations. So here we go. So right here, these are all the possible truth combos. It shortens down to this. All are true, all are false, or mixing and matching. Okay. Now there's a way to do it here that's pretty straightforward. Like I said, I'll post a PDF on how to do it. Basically, if you have, you double the amount of pieces that you have, or how many lines that you're going to have to make all the possible combinations. So those are the parts. Then let's look at the premises. So here we have A arrow B for the argument. That's premise number 1. Premise number 2, just A. And our conclusion is B. So we got these pieces. So I have a choice here. So this way I'm going to do it the long way just to show you, but I don't have to do it the long way. So the long way is wherever I have A's and B's, once I have set what the possible truth values are, I can copy them over. So this is the long way to do it. So wherever I have an A or a B, I'm going to copy it over. All right, so A, I'm going to copy what I have in A over here. T, T, F, F. And wherever I have a B, I'm going to copy it over here. TF, 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 TF. Now, in a minute, I'm going to show the shorthand way to do this, too, where I don't have to do this. Okay? So then what I want to do is figure out what are the values for the actual lines here themselves. So this stuff over here was just for the pieces. Okay? This stuff really doesn't matter in the scheme of things to the left. Let's put it here to figure out what the pieces would be. So here, I've got premise 1, premise 2, and a conclusion. Okay? Now here, something's missing. This arrow means something. I need to figure out what the arrow means. What are the values for the arrow? That's what this premise would be, or what the values would be in here. But if I go back and take a look at the arrow rule, the arrow works this way. As long as I've got, let me put it this way. The only time an arrow rule doesn't work is when I have a true left and a false right. So what's the only occasion here that an arrow does not work or yields a false? Right here, true left, false right, that doesn't work. All the other instances work. And so these values right here, this column, is indicative of the first premise here. Okay? These are the values for this. Now since these are simple, these values that I have here are fine. Okay, great. Now what do I do with these values? Well, this goes back to something that I actually said on quiz 1. What makes an argument valid? An argument is valid if and only if, and that's a double arrow, given that the premises are true, or T, the conclusion, the thing you're trying to get, this thing must be true. Alright, so this is the definition of validity. This is actually going to be important here. Let's take a look here. So what we want to look for, what are the premises in this argument? Arrow out. Well, premise 1, premise 2, and then we said this is the conclusion, right? Well, so let's look at premise 1. What are all the instances in which all the premises are true? And I'll go, for the sake of making it easy here, I'll label these lines 1, 2, 3, 4. Okay? In line 1, look, we got a true in premise 1. We have a true in premise 2. Okay. Let's look at line 2. We have a false in, well, that doesn't matter because the premises, one of the premises isn't true, so we're not going to worry about it. Let's look at here. Line 3. One of the premises is true, but the other premise is false, so we don't need to worry about it because we're only caring about when all the premises are true. Let's look at the 4th line. Premise 1 is true. Second premise is false. It doesn't matter. Take a look here. For this argument, according to this little table here, when the premises are true, what's the conclusion? It's also true. There are no exceptions to this. Yeah, there's some instances where, all right, one of the premises is false. Those don't matter. Look, we got all t's. So when all the premises, all right, so the premises here, we have two things leading up to it. That's what I mean by premises here. Look, when all the premises are true, look, the conclusion is true. This means the argument is valid. This means it works, and we know it works. It's arrow out. But now, does this work? A, arrow B. B, can you get A? Question mark. Can you get it? Well, the answer, I'm going to go ahead and tell you, no, this doesn't work. In fact, this is a fallacy called affirming the consequent. It doesn't work. Well, Professor Burris, just because you say so, how do I know it doesn't work? Well, watch this. I'm going to do the exact same table here. I'm going to take my A and B. Okay. Possible combos. Possible truth combos. TTFF. TFTF. We take my premises, A, arrow B, for premise number 1, premise number 2, B, and then my little conclusion that I'm going to try and go for is A. And so what I'm going to try and see is, does it work here? Or when I have all truths in the premises, do I get a true conclusion? Well, let's see. Well, first of all, like I said, long way, I can copy just these things over. All right, so wherever I see an A, I'm just going to copy this over. Wherever I see a B, I'm going to copy this over. And like I said, there's actually a simpler way to do this that I'll do on another problem. But for now, I'm just going to copy over what I have. All right. Premise 2 is complete. The conclusion is complete in terms of values. But here, I'm focused on the arrow. Now, in order to calculate what the arrow is, the only time an arrow doesn't work is when I have a true left and a false right. So here it's false. All the other times are true. All right. So this column here is the only column that matters. This represents the values for premise 1. So let's see. Do I have an instance when all my premises are true? Yep. Yep. Line, like, look, my line 1, 2, 3, 4 here. So look, my line 1, my premise 1, true. Premise 2 is true. Okay. Hold on to that. I have another instance, and this time, this wasn't true over here, but in line 3, look, I have my premise 1 is true, and my premise 2 is true. Cool. And then in these other scenarios, in line 4, now I've got a false. In line 2, I have a false. So I'm only looking for all lines where my premises are true. So line 1, this works. Line 3, this works. Now what I want to look for is over here in the conclusion column, is my premise also a true here? Basically, I'm looking for, does it match throughout in all the pieces? So look, this line 1, premise is true. It works. But in line 3, I've got a true premise number 1. I've got a true premise number 2, but I have a false conclusion. What that means is that my argument is invalid. And if I went back and looked at quiz 1, an invalid argument is where, given that the premises are true, it's possible for the conclusion to be false. So this argument doesn't work all the time. It might work sometimes, but here, when does it not work? And it actually gives us the occasion to tell us its counter-example. It tells us exactly when it doesn't work, and what you do is you look at the values of A and B in this row. What is A every single time you see it in this row? Look, A is false, A is false, A is false. So every time in this row, A is false. What is B every time we see it in this row? True, true, true. So two ways of writing this. I could say the counterexample for this is when A is false and B is true. So this argument doesn't work, and it's invalid, and here is the instance in which it doesn't work. Right here. When A is false and B is true, this does not work. So consider this, like, if you work, you get paid. I got paid. Oh, so you must have worked. Well, no, it doesn't work if you didn't work. Like, say you won the lottery. Oh, I didn't work, but I still got paid. I got a check. Well, then this argument doesn't work here. And that's what makes this false here. And it even tells us when it doesn't work, when the argument is invalid. And that's exactly what a table does. It tells us, here's why this doesn't work. It's not because you didn't know there wasn't a rule for it. It doesn't work because it doesn't add up. It's invalid. There's an instance when if you had all true premises, you get a false conclusion. That's stupid talk. That means there's no proof for this. You could not solve a proof for this. No proof exists. And that's what a truth table allows you to do. And this is what a truth table is. Truth trees allow you to do this as well through another method. So let's take a look at some more tables and see if we can figure out the validity or invalidity of particular arguments. Now hopefully you can see this is a hypothetical syllogism. A leads to B, B leads to C, A leads to C. We've had this kind of stuff really laying around since quiz 3. We have 3 letters here, and so 3 letters requires us to do a little bit more to figure out what all the truth combinations are. And so I'm going to do that for us here. That means we've got this. We've got 3 letters, A, B, and C. And so we got 3 letters. That means we're going to have 8 lines of possible combinations. So here's what you do. I know for what if I have 2 letters, I'm going to have 4 lines. If I have 1 letter, I'm going to have 2 lines. If I have 3 letters, I'm going to have 8 lines, and it doubles with every increment there. So if I have 4 letters, I'm going to have 16 lines. If I have 5 letters, I'm going to have 32 lines. And then what I just do is I know, okay, so I've got 3 letters, I'm going to have 8 lines. Then what I do with my first letter is I go ahead and take that number 8, and I divide it in half and immediately put, okay, I'm going to have 4 possible T's and 4 possible F's. And then I take that number and I have it. So if I had 4 T's and 4 F's, then I'm going to have 2 T's, 2 F's, 2 T's, and 2 F's. And then I take that number for my next letter and I have that. So half of 2 is 1. So I'm going to have TF, 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 TF. And it doesn't really matter what letter I put these on as long as I'm consistent in application. And actually this time I'm going to do it the short way. So let's say I had this. So this time I'm going to do it the shorter but just as legitimate way. Let's take my first premise. So remember this here, these are just my constituent components. These are just labeling my parts. So this is just over here for me for free. Premise number 1, A arrow B. Okay, I'm going to put a little 1 up here. Okay, that's premise number 1. Premise number 2, B arrow C. Okay, that's premise number 2. Conclusion, A arrow C. Okay, that's my conclusion. Okay, so this is going to be, I'm going to consider this one separately in a way. So I'm going to consider these in different ways. Remember, if I have all T's for these, and then I have a T for this one, in every instance it's valid. If I have one exception to that, where I have all T's over here, but an F over here, it's invalid. Well, a hypothetical syllogism works, so this should be valid. So the way this should work is every time I have a T for this column, and every time I have a T for this column, I should have a T for this column. That's how validity works. So what I'm going to do here, rather than, now here's what I could do. The long way to do this is every time I have an A, I could just transpose this over. Wherever I have an A, I could write all the A, T's, and F's. Wherever I have a B, I could write all the B, T's, and F's. Wherever I have a C, I could write all the C, T's, and F's. Instead, to make it a little bit easier, I'm just going to refer to what I have over here and put it in. So for the first premise, this is what I'm trying to figure out. Okay? The values of the arrow. And the way an arrow works is this way. The only time it doesn't work or yields a false is when I have a true left and a false right. So what are the values that I have in here? A and B. So I'm just going to look at these A and B columns. And the only time I'm going to put an F is if I have a true for A and an F for B. All the other ones are going to be true. So let me just go down it this way. Let's see. I'm just going to look for my, basically, T on the left and F on the right. So that doesn't work. Line 3 doesn't work. Line 4 doesn't work. And these are all F's. So all the other ones work. This one works. This one works. All these other arrows would be things where they work just fine. Okay? Same thing here. I want to figure out the values for B arrow C. So what I'm doing is I'm looking at the B and C values, and the only time I'm going to stick an F in here is where I have a true left and a false right. So where does that happen? Line 2. That one doesn't work. Both those start with F, so that's fine. And look, line 6, this one doesn't work. All the other ones are good. So I'm going to fill those in with T's. Alright, so look, these right here are the values for premise 1. All the possible values. These right here are all the possible values for premise 2. All the premises are done. So now I'm going to look at the values for the conclusion. And so here, and this is where I'm using the shortcut method, now I'm not comparing A and B, I'm not comparing B and C. This time I'm comparing A and C. So this column here for A, and this column here for C, and the only time an arrow doesn't work is when you have a true left and a false right. So let me go, I'm looking at these two columns and filling it in here. Again, if I wanted to do it the longer way, I could just copy the A over here, and I could just copy the C over here. To save myself some time, I don't want to do that. I'm just going to refer to what I have over here. So this time, since it's a little bit more distant, I'm going to do it line by line. So true into true, that works. True into false, no. You have a false right, that doesn't work. True into true, yep. True into false, nope. And all these start with false, so there's not the only time it doesn't work is when you have a true left and a false right. So if it starts with a false, I know it's going to work. So here's all the values for my conclusion. Cool. Now here's what I want to do. I want to look at it this way. So I'm going to look at my premise 1, my premise 2. What I want to look for, all values where I have T's that match up for line 1 for my premises. So this one's my conclusion. So first of all, I'm going to look at my premises, where I've got all T's. If the argument is valid, then for my premises, I'll have all T's, and the conclusion will also be T. If the argument is invalid, I want to look for the lines where I have all T's, and then also I have an F somewhere. If that's the case, on some line, it doesn't have to be all of them, it could be just one of them, I've got all T's and an F somewhere. So let's see what's going on here. Let's take a look at it row by row. So look, all T's. Okay. Nope. There's an F here. There's an F here. All T's. There's an F here. All T's. And all T's. So really, the only rows I care about are the ones where you see all the T's here. So this one I care about, this one I care about, this one I care about, and this one I care about. So what do I have over in the conclusion column? Here I've got a T as well. Here I've got a T as well. Here I've got a T as well. And here I've got a T as well. Here's what this means. In all instances where the premises are true, the conclusion is also true. This means that the argument is valid. It works all the time. So we've got our next argument here. It's S XOR B, S arrow D, B arrow Q. We're solving for D arrow Q. We want to see, is this argument going to work or not? It's got 4 variables. This is the largest kind of one we're going to do. If you have a situation where you have 4 variables, there's going to be 16 possible combinations of T's and F's. You notice it's all T's here, all F's on the bottom, and what you have in between, those other 14 lines, are all the other possible combos. So the way that I do this is I take my first letter, whatever it is. I could have put these alphabetically. As long as I'm consistent in application, it doesn't matter what letter I apply them to. But I take my first letter, the first one that I saw, I'm going to take 16 divided by 2. So I'm going to have 8 T's and 8 F's. Then I'm going to take that and divide it by 2 and spread it out. So I've got 4 T's, 4 F's, 4 T's, 4 F's. Then I'm going to take that and divide it by 2. I've got 2 T's, 2 F's, 2 T's, 2 F's, 2 T's, 2 F's, and so on. And then take that and divide it by 2. I've got TF, 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 TF. And like I said, I could apply these to any letters as long as I'm consistent in my application. I could have done them alphabetically or whatever. I've just done them in the order that they come. So that's fine. So I'm going to use this here as a placeholder, and then I'm going to use those tree rules in each of these instances. This one's actually pretty easy in terms of the way it's been laid out, because there's no squiggles in here, there's no negations. I'm able to just apply these standards and put them here for each of these premises and the conclusion. So let's start with the first premise. The first premise is between S and B. So I'm going to take a look at this column and this column, and I'm going to look at the rules for XOR. And the XOR rule says this: it only works if you've got one T and an F. If you have any duplication, you got all T's, you got all F's, it doesn't work. So for example here, this first line, you got between S and B, you got two T's. Nope. An XOR, only one can be true. It's going to be one or the other. So that one doesn't work. Actually, the first four here are actually all where both are true. Nope, none of those are going to work. Okay? Then the yep, the next batch all work. They've got where the left works. The next batch works because it's got where the right one works. So FT, 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 FT. Yep. And then the last batch are all F matches for S and B. And so that means no, if anytime in an XOR you got to match both sides of the same thing. Nope, that doesn't work. This one's done. These are the values for premise 1. Now with the same criteria, let's take a look at the values for premise 2. This is S arrow D. Now remember the rule for arrow, on the other hand, unlike XOR. XOR was that you got to have one or the other. It's got to have one T, one F, one T, one F. The way I want you to think about arrows, and the next three are arrows, both the next two premises and the conclusion, so we're going to be applying the same rule. The only time an arrow does not work is if you have a true left and a false right. So what we're going to be doing is we're going to be looking for the second premise. We're going between S arrow D. So we're going to look at this column and compare it to this column, S and D. So when we have a true left and a false right, that's the only time it doesn't work. All the other ones are going to be T's. So we're looking at S and D here. Yep. Yep. Nope, because there's an F on the right side. Nope. Yep. Yep. Nope. Nope. And anytime it starts with an F, you automatically know it's going to be fine. So the rest of these are going to be T's. Alright, we're good to go. Okay, let's now take a look at the third premise, B arrow Q. So I'm going to be looking at the columns here, B and Q, and see what I get. So this first one here is going to be true. This one's going to be false. This one's going to be true. This one's going to be false. This one's going to be true. This one's going to be true. Yeah, anything that starts with false is automatically going to be true. So this one's good. This one's not good. Good. Nope. And then the next four start with false, so they're all going to be good. Alright, let's take a look at the last one. The last one I'm going to look at, the conclusion, I'm going to look at D and Q. We'll be looking at these two. So while I'm looking at D and Q, let me fix that one back. I'm going to be looking through them. So true, true, that one's going to work. Not going to work. If it starts with false, it's good. That works. That one doesn't work. That one works. That one works. That one works. That one does not work, again, because it has a true left, false right. And the next two start with F, so they're going to be fine. And then the last four, this one's good, this one's good. And then the last two, we've got a nope and a yep. Alright, so we're good to go. The argument is complete in terms of filling it out. Now let's see if we can figure out the validity. So what I'm going to look for is where I've got all t's in the premises. So I have 3 premises. 1, 2, and 3. I'm going to look for where I have all t's here. So if I start with an F, I don't care. Nope, nope, nope. All right, so here's a T. This is the 5th row. So T, T, oh, I've got all t's in the 5th row. All right, so this is a premise of interest. I've got all t's in the 6th row. This is a premise of interest. So we're all t's. So that's what you want to look for. Look for in the premises where you have all t's. So TF, I don't care. TF, I don't care. T, T, T. Oh, so this one's important too. All t's. TTF, TTT. All right, this one's important too. All t's. Okay, TTF, no, F, or if it starts with F, I don't care about it. So really, these 4 rows that I've identified are the ones that are important. These are where all the premises are true. Okay, row number 5, row number 6, 9, and 11, the way that I've itemized them. Like if you did some different stuff over here, you're going to get the exact same things. As long as you're consistent in your application, you get the exact same things just in different rows. So what we're going to look for is, what do we have over in the conclusion? On the same row. If you have in these 4 instances, if you have all t's over here, the argument is valid. If you have even one F over there, the argument is invalid. And it will also tell us the counterexample. So let's see. So let's look at row 5. T, T, T. So 5th row. What do we got over here? T. Ah, that's good. 6th row. T, T, T. But what do we have? An F. That lets us know automatically this argument is invalid. There's no proof for it. It doesn't work. But let's keep going. T, T, T. We get a T over here as well. And then this one, T, T, T. We get a T over here as well. So it's invalid, and we know there's one instance that shows us exactly where it screws up. And it's this instance. So it's for us in this permutation, the 6th row down. So what are the conditions in the 6th row down? 1, 2, 3, 4, 5, 6. So in the 6th row, when S is true and D is true, but B and Q are false, it doesn't work. So there's 2 ways of putting that. We could say this is the counterexample. We could say we could put it out this way: S, B, and D, Q. And in that situation, we could say when S is true and B is false, and when D is true and when Q is false. That's one way we could put it. The other way you could put it is say this way. You just say the same thing, but when you want to say false, you just put a squiggle in front of it. So the other way of rendering a counterexample is saying S, squiggle B, D, and squiggle Q. That works as well. So the counterexample is this. In this situation, this doesn't work. That shows that this is not valid. But as you can see, like, this table is huge. This takes a long time to fill out. It's hard to keep all the lines in a row. Like I said, you could do this in an Excel spreadsheet and make it much tidier, but this takes a long time. It works, but this demonstrates the flaw of the table method in that, the more variables you add, the longer that it takes. And this is why the tree method exists. So sometimes the tree method is technically called the semantic tableau. What I'm going to do next is show you how to do what we've done so far with the tree method, and show you how the tree method is much simpler to do. The tree method has some flaws too. It has some problems as well. Okay, so when you have multiple counterexamples, the tree will always show you whether or not the tree is valid or invalid, but it doesn't always show you all the counterexamples, depending on how you do it. So it's not as succinct in showing you all the counterexamples. But we're going to do that next. So again, this is as big of a table as you're possibly going to have on your Quiz 9. But we're going to look at everything we've done so far. We're going to do the exact same things, just with the tree method, and see what we learned thus far. Then I'm going to practice some problems side by side and take a look at how do we do it in the table method, how do we do the tree method side by side. So let's start by looking at what the tree method is. All right. Everything you see here are the rules for trees. So basically, there are three kinds of tree rules. Those that stack, and these are knots, ands, and nors, and narrows. And then rules that split, ors, arrows, and nans. And then rules that split and stack. Those are double arrows, double narrows, XORs, and XNORs. And so what you want to do is you want to find the top situations here first. Where are situations where this stuff is going on? The stack rules, if you can do a stack rule, do that first. Then do the split rules, then do the split and stack rules. So have this sheet next to you, the tree rules for propositional logic, for what to do. And then let me show you now how to do a tree instead of a table. And like I said, I actually think trees are, I prefer trees to tables, but they take a little bit more to get used to. Obviously, there's more rules to know, but once you know the rules, like I said, I think the trees are actually easier than the tables. They definitely take less time. So let me show you how to do a tree, and we're going to start with the two problems that I began with the tables. All right, first of all, let's take a look at this argument. Modus ponens. A arrow B, A, B. Now I already have the table up here, and we know according to the table combination, it says that when you have all true premises, you're going to have a true conclusion for A arrow B, A, then B, so you know it's going to work according to the table method. Let's take a look at the tree method. So here's what you do with a tree. So with a tree, you line up the premises and the conclusion like this. So you stack them like this, and then for the conclusion, it almost works like an indirect proof. You negate the conclusion. And then anything that needs to be broken down, you break it down, especially in the order that I suggested according to the rules. If it's a rule that stacks, do the rule that stacks first. If it's a rule that splits, do the rule that splits second. If it's a rule that split and stacks, do that next. So let's see, can this be, now that we've negated the conclusion, can this be broken down anymore? Nope. Can this be broken down anymore? This one? Nope. Can this be broken down anymore? Yes. This is an arrow. And if you look at the rule for arrow in the tree rule, it says here's what you do. You take it and you split it like this. It splits, and basically what you're doing is the material implication rule, the MI. So remember, if you have an arrow, you can turn it into an OR by negating the left side, and just that alone. So this wedge here, a split rule is basically like a giant wedge where the wedge is upside down. That's all it is. So what does an arrow turn into? It turns into squiggle A and B. And then here's what you do. You can think of this as like, this is flowed downstream. Everything's been broken down. This has been broken down. Look back up the line and see, do you have opposites in these tributaries, in these streams that are flowing downhill? So look here in this one. We've got squiggle A. Are there opposites in this stream? Yeah, look, A, squiggle A. So what I do is I put the symbol, which means, yep, contradiction. This works. Do I have contradictions in this stream? Yeah, B and squiggle B. And look, we've broken down everything, and everything results in a contradiction. Like all the tributaries break down. This means the argument is valid. Nothing is leaking. Everything's good. And we know it's going to be valid because it's arrow out. But now let's take a look at the argument that's very similar to this, but is not identical. The one that we said was a problem earlier. Let's take a look at it using the tree method. Okay, the next argument is going to look like this. Let's take a look at A arrow B, next premise B, and then it leads to A. Now here I've already actually copied the table over. We know this method does not work because if I fill in the table, yeah, there's an instance where when the premises are true, the conclusion is true, but there is actually one scenario where the premises are true but the conclusion is false. This means that the argument is invalid, and the table actually tells us the scenario in which It doesn't work. When A is false and when B is true, it leads to true premises and a false conclusion. And so in that situation, A was false and B is true. Now I can write it this way. This is one way of writing it, or I can write it this way. Either way, they both say the same thing. When A is false and when B is true, this argument does not work. So those are the conditions in which this argument does not hold. There's no proof for this argument for this reason. So that's the table method. And like with small tables, it's pretty easy. I think this, when we got a short table like this, just two variables, it's fine. The tree method is a little bit quicker, but I think we'll see that when we get to larger problems, the tree method is much more effective. So let's do the tree method here. So the first thing you do with a tree is you stack your premises like this. Here's the argument. Okay, premise 1, premise 2, and the conclusion. Then the first thing you do is negate the conclusion. And then what you do is you see if anything can break down anymore. So you see, can I do any stack rules, any split rules, any split and stack rules? So this can't be broken down anymore, this can't be broken down anymore, this can, and we just did this a moment ago. What this does is arrows split, and basically what you do is it's kind of like doing the material implication rule. You're basically turning it into this with, you could think of the split as a giant wedge that's been turned upside down. So what does A arrow B turn into? It says if you got an arrow, split it, and so make two tributaries, and take the left side and negate it, and take the right side and keep it the same. Alright, great. Now what you want to do, every time you do a move in a tree, so we broke this one down, look up the tributaries and see, do you have any opposites in each segment? Do I have any opposites here? I do not. So the symbol we write here, make like a little arrow pointing upwards. No, there are no opposites here. Do we have any opposites in this one? No. It happens twice. So look at A every time you see it in this segment. What is it? Is it A or is it squiggle A? Alright, so what that tells us, if you have no contradictions in a segment, that means the argument is invalid, which confirms the tree, by the way. But then we can also get the same counterexample. What is A every time we see it? Does it have is it regular A or is it squiggle A? Oh, it's squiggle A. What is B every time we see it in this whole tributary, looking all the way up to the top? Every time we see something broken down, we see squiggle A and B. Regular B. In this one, what do we see? Squiggle A and B. So look, what this got us is it told us the argument is invalid, and it also told us the counterexample twice. What it's saying here is when everything's broken down, you get squiggle A and B, it doesn't break down to a point where it gets contradictions. It doesn't break down. It told us twice that squiggle A and regular B is the counterexample, which matches what we got in the table. We get the exact same counterexample. So that's what the tree does with the table. It's another method for showing if it's valid or invalid. It gets the same results. Now, one disadvantage to the tree is sometimes it doesn't get as many counterexamples as the table. So that's something that does occur, where it doesn't always show up in the tree when it does in the table. That's never going to be an issue on the problems I'm going to give you. If they show up in the tree, if it shows up as invalid, all the counterexamples that show up are going to show up in the tree as well. So if they show up in the tree, they're going to show up in the table. If they show up in the table, they're going to show up in the tree. That's the way that Quiz 9 and Quiz 10 are going to work. So let's do another tree on a problem that we did earlier as well. All right, let's take a look at this argument. A arrow B, B arrow C, therefore A arrow C. I copied the table here. Let's do it the tree method. Okay, so what we do is we copy down all the premises, A arrow B, B arrow C, and then A arrow C. And then what we do is, for the conclusion, we negate the conclusion. So not just the left side like this, we negate the entire thing. And now we apply the tree rules. So remember, first we look at what rules stack, what rules split, and then what rules split and stack. So here, do we have anything that stacks? We do. This one basically does the conjunctive conditionality. It turns into this. It says if you have a not arrow, it's basically So in this situation, it's basically the same thing as having this, as if it were broken down. So that's exactly what the narrow rule says. You stack, if you have an arrow with a knot on the outside, a narrow, take your left side, keep it as it is, take your right side and make it the contrary of that. So that, all right, so this one's broken down. And so every time you break something down, look, do I have a negation yet? Do I have two opposites? Nope. All right, so then go back to the top and apply the rules. So I've got two arrows here, so these are both going to be split rules. So take a look. Let's break this one down. Arrow says you split it. You take your left side and put a knot in front of it, and keep the right side as it is. All right, this one's broken down. So now what we do, we look in this line and see, are there any opposites in this line? Well, yeah, A and squiggle A. So this line stops. It's done. Now let's take a look at this one. Okay, this line's still open. Stuff is still flowing here. Here you can say the leak has been stopped. Valid arguments always close down. There's no leaks. Invalid, there will be a leak where it won't close off. So we've broken this thing down, and these things are broken. They can't break down anymore either. Let's take a look at this one. We got B arrow C. Now it's an arrow. If you look at the tree rules, it says what you do with an arrow is anything that's still open, something that's still flowing, you apply the rule there. So for here, that means here, we're going to get squiggle B. All right, because the rule for arrow is take the left side, squiggle it on a split, and then the right side, keep it the same. Okay, so now we have two tributaries open, this one and this one. Take a look what we got here. Any opposites here in this line? Yeah, B and squiggle B. So this one closes down. And what about this one? Yep, C and squiggle C. This one closes down. Look, everything's broken down now, and every place where something is flowing, there is a contradiction. There are opposites, A and squiggle A, B and squiggle B, C and squiggle C. This means if everything closes down, it means the argument is valid, which is something that the table already told us, but the tree tells us a little bit more quickly. Okay, you got to know some more rules to figure it out, but it tells us the exact same thing. Everything closes down, no leaks, argument's good. Let's take a look at the next one that I went over. Here's the next argument that we did with a table. Now, the table was so big that I don't have the space to copy it over. But I will say this, if you go back and take a look at it, you'll see that we got this as a counter. We got that this argument was invalid. All right, it's not going to work because it's going to, in the tree, it's going to leak. But we also got the counterexample is this. The counterexample is this. S is true. Squiggle B is the case. So when S, not B, D, and not Q. So this is the combination that makes this not work. We got that at the table. Let's see if we can get it in the tree as well. So here's the tree. We got everything that we could possibly have stacked. Then what you do is you negate the conclusion. Is this sufficient? No, because we're negating the whole conclusion. Then what you look for is, remember, there's in a tree three kinds of rules. There's stack rules, basically things that turn to and outs. Split rules, basically things that turn to ors, and split and stack rules, where you do both. Those are XORs, XNORs, double arrows, and double narrows. So do we have any of the stack situation? We do. We have a narrow, a not arrow. What happens in that situation? It's basically like you're doing conjunctive conditionality. So what you do there is when we're breaking this one down, we're going to keep the left side as it is, and we're going to negate the right side. Okay, so this one is broken down. Do these break down anymore? Nope, they're good. All right, let's take a look up the trunk. Any contradictions? Nope. Okay, so all our stack rules, at least at present, are done. Do we have any split rules? So go up the tree and go to the top and see what's the next thing that I can do. So I could do this, but this is a split and stack rule. It's an XOR. I'm going to save that for last. Let's do this one then next. It's S arrow D. The way the arrow rule works, it's a split rule that says you make the left side a squiggle, the opposite of the left side, and you keep the right side as is. Okay. This line's done. This thing's broken down. So first of all, take a look here, Any opposites up this tributary? Not that I can see. Any opposites up this tributary? Not that I can see. Okay, so we break down the next thing. So let's see. Any more stack things that we can split, that we can break down? No. Any more split rules that we can do? Yeah, this arrow. But this arrow, it's B or Q. It's the same rule that we just did a moment ago. When you break down an arrow, you squiggle the left side, or you make the opposite left side, and you keep the right side as is. But this thing is flowing down this way. It's flowing into this, and it's flowing into this. So since it's flowing into both, we have to demonstrate that. So it's flowing downstream into this. That means you split it here, squiggle B, Q, but it's also flowing down into this as well. Squiggle B, Q. Alright, so this thing's broken down. Now what we do is see, alright, do we have opposites here? Opposites in this tributary? No. Opposites in this tributary? Yes. Q and squiggle Q do not get along, so this one's shut. This valve closes. This one? No, this valve's still open. This one? Yeah, this valve closes as well because of the Q and squiggle Q. Alright, so this one's still open. This one's still flowing. This one's still flowing as well, and we got one more thing to break down. S XOR B. So the way that the rule for XOR works is this. When you have an XOR, it splits and stacks. Basically into one's good and the other's not, or that first thing is not good and the other is. That's the split and stack. So that's what's going to happen here, except with S XOR B. So here's what we got. Splits down to this. We get S and squiggle B. This one gets a contradiction because we are S and squiggle S, so this one does not work. It shuts down. That's good. And then here we get squiggle S and B. This one shuts down too because of the B and the squiggle B. So this one shuts down. Okay. This one we don't need to apply anything here because we've already figured out it has a shutdown. This one has a shutdown. So this is the only tributary that's still open. And the application here is going to be identical to what we had here. We're going to get S and squiggle B, and we're going to get squiggle S and B. Let's take a look. Any contradictions? Alright, in either one of these branches. This one, yep, it has a problem. B and squiggle B. So this one breaks down. This one, though, take a look at it. Are there any, where everything's broken down, do we have any opposites of any kind in this tributary, in this particular stream? No. So that means I'm going to write this little symbol here, this arrow, and take a look at what everything is in there. So we've got four things. We've got S, B, D, and Q. Look what S is every time we see it. It's just regular vanilla S. Okay, there's S. I only see it once. What is B every time we see it? Look, squiggle B, I don't see it any more times when it's by itself, so squiggle B. What is D every time we see it? Well, just regular D, twice. It's there twice, so regular D. And what is Q every time we see it? Is it Q or is it squiggle Q? I only see it once and it's squiggle Q. So take a look. What this is saying here is when you have a branch that won't close, it won't close down. One, that means that the argument is invalid. But then the pieces of the argument, the little constituent components, also tell us the counterexample. Sometimes there can be more than one, like in a table. But look, it says when S is true, when B is false, when D is true, and when Q is false, this argument, it will leak. It's invalid. It won't flow. And look, so we get this. Here's the counterexample for the argument, and notice it is exactly what we got in the tree as well. Same thing. The argument is invalid, and it tells us when it's invalid. So that's what you're going to have to do for quiz 9 and quiz 10. Not only if an argument is invalid are you going to have to say that it's invalid, but you're also going to have to say what the counterexample is. Let's take a look at an argument like this. So I'm going to do it the table way, and then I'm going to do it the tree way. So this is an example of De Morgan's law. If you've got like an and statement, you can turn it into a wedge statement. Just you flip all the negation slots. And let let me show you the parameters of that. So a rule of substitution always works like this, always. Let's take a look at the AND. Let's fill in the values. The only time an AND works is when all the parts are true. So we got the A and B values, so it works, and then it doesn't. Okay, now let's fill in these values. So I'm not going to copy A and B over, but I am going to make my squiggle A would be this. Nope. Nope. Yes. Yes. Squiggle B would be nope. Yes. Nope. Yes. Squiggle A would be whatever the opposite of A is. Squiggle B would be whatever the opposite of B is. And then the way an inclusive disjunction works is as long as I have one T, we're good. So nope. Yep. 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 But the main operator here is actually this squiggle. So to figure this out would be to say whatever the opposite of this is. So it would be true, false, false, false. The opposite. So the main operator here, and the main operator in this premise was the conjunction. The main operator here is this. So this is really what I'm working with. And this is really what I'm working with. And you'll notice here that the premise and the conclusion, because all this other stuff was stuff I used just to get there. It's not wrong, but stuff I used to get there. You notice it's an exact match. When you have a match between a premise and a conclusion, that's when you got a rule. So this is how De Morgan's law works. Look, wherever there's T, it's a T. Wherever there's an, like, it's the exact same thing. So whenever there's a match, that's the way a rule of substitution works. You're going to have an identity between them. That's why I can say A and B and squiggle A, wedge, squiggle B are the same thing. They have the exact same truth content. Let's do the tree for it and see what we get. We get A dot B, and then we get squiggle A, wedge, squiggle B. Okay. Now remember what we do with a tree is we put a squiggle on the conclusion. So we're going to get an extra squiggle here. And then we're going to do our rules. So the first rule I see that I can do is actually the double negation rule. This one is going to break down into this. Squiggle A, wedge, squiggle B. Alright. So that's broken down. Then I see, do I have stack rules? Yep, this A and B is going to break down into this. And then I have a split rule. This thing is going to split into this. The way a split rule works is when you get a wedge is you just split it and you keep each part as it is. Squiggle A, squiggle B. And take a look in this tributary. Do I have opposites? Yep, A and squiggle A. This one breaks down. Do I have got B and squiggle B. Everything has an opposite. When you have everything plugs, this means that the argument is valid. So in the table, it's whenever you have a true premise, you get a true conclusion. And I could flip this around because, look, they're identical. If I flip this around as my premise and turn this as my conclusion, it's going to be the same thing. Alright, same thing in reverse. I went ahead and plugged in the table here, and look, there's an identity between the premise and the conclusion, like TFFFF, TFFF. It's the same thing. That's why it's a rule. That's why this De Morgan's law exists. So I'm going to take the same thing here, and look, I'm going to get squiggle A, wedge, squiggle B, and A and B. And the first thing we do in a tree is we negate the conclusion, the whole conclusion. So this is squiggle A and B. And then we take a look at the rules and see what we can do next. Do I have a stack rule available? We do have a stack rule available. We have a NOR, and a NOR says this. What you do is basically you do De Morgan's law and do an AND out. If you have an OR, an inclusive disjunction with a not on the outside, you take your left and right components and you stack them as the opposite of whatever they are. So that means we get A and B. This one's broken down. Then the next rule we've got is a split rule. All right, we have a NAND. We have a not AND. And the way that one works is it says it splits, and you put a squiggle on each the left and the right side as it splits. So we get squiggle A and squiggle B. And take a look. Opposites in this chain, this tributary. Yep, this one breaks down. Squiggle A and A. This one breaks down too. B and squiggle B. What does that mean? The argument's valid. Which is exactly what the table tells us. When the premise is true, the conclusion is true as well. There are no counterexamples. And since we saw in the previous table, in the previous tree, it works the other way. This is why we have a rule, De Morgan's law. Let's take a look now at why we don't have a rule that allows us to turn ands into XORs, for example. All right, let's take a look at it this way. Can we turn an and into an XNOR? And actually you can. Look, when it's true, the conclusion is true. There is no exception to that. So you can turn A dot B into squiggle A, XOR squiggle B. Well, hey, Professor Burris, you said this isn't a rule. You said this is something we can't do. It's not a rule because it works this way. You'll see. Take a look. Let's do the tree for it. It works this way. So we got A and B, and then we're going to do this. We're going to do squiggle A, XOR squiggle B. The first thing we do in a tree is we squiggle our conclusion, which means this is going to turn into squiggle A, XOR squiggle B. Then that's broken down because we've turned it into this. First thing we're going to do, we got a stack rule. We got A and B. Next thing, this is a split and stack rule, and the way that XOR works is we say this: as it is, and the other one, the opposite, and not as it is. So take a look. In this branch, do we have contradiction? Yep. Squiggle A and A. In this branch, do we have a contradiction? Yep. B and squiggle B. Now this argument's valid. So if you've got A dot B, can you turn it into squiggle A, XOR squiggle B? Sure. So why don't we have a rule for this? Because it doesn't work both ways. Because watch, we're going to do the same thing in reverse, and it's not going to be valid. Let's take a look. Let's take a look at the same problem in reverse. Look, when we put it this way, squiggle A, XOR squiggle B, we want to get A and B. So look, yeah, we got a true premise. We got a true conclusion. I remember when we started it, we started with this and it worked this way. That was fine. But then we get another true premise here and a false conclusion demonstrating this argument is invalid. And it's invalid here on this line when A is false and B is false, or another way of putting it is when you get squiggle A, squiggle B. This argument doesn't work. So let's put it in tree form. Let's do it the tree way. We get squiggle A, XOR squiggle B, and we get A dot B. First thing you do in a tree is take your conclusion and squiggle it. So now, do we have any stack rules that are going to apply here? No. The first rule that we're going to have is a split rule. So we have a NAND. The way NAND works is it basically splits like we're doing De Morgan's law. We get squiggle A and we get squiggle B. Okay. Then we have here an XNOR. How does an XNOR work? Let's take a look. XNOR works this way. What you do is if you have a XOR with a squiggle on the outside is you do this. Now it's going to flow down into here and into here. It splits and stacks into this. Basically the way that an XNOR works is this, is when you have an XNOR, you on the left split you keep things exactly the way as they are, and then on the right split you do the contrary of that, and it's going to flow down into both. So we're going to get this. You keep things exactly as they are, and then the exact opposite as they are. Alright, so let's evaluate. Do we have contradictions? This one? Nope. This one's open. This one? Yep, that closes. This one? No, this one's open too. And this one closes. So look, we have two ones that are open. Let's take a look at this open one first. Look, it's what is A every time we see it? Squiggle A. What is B? Squiggle B. Let's take a look at this one. What is A every time we see it? Squiggle A. What is B every time we see it? Squiggle B. So it tells us this argument is invalid. And what's the counterexample? Squiggle A, squiggle B. That is exactly what we got with the table. Same thing. it's invalid, and the counterexample is squiggle A, squiggle B doesn't work. That's why there is no rule. There's not a special de Morgan's law that allows you to switch from AND to XNOR. It works in one direction. It doesn't work in the other. That's why it's not a rule of substitution. It doesn't work. It's not a thing. Let's take a look at another. I'm going to put the same thing I've got here in an Excel spreadsheet, and I'm going to go ahead and do that now. So here you go. Here's a tidy version of this. All right, so rather than an Excel spreadsheet, this is actually a table in Microsoft Word, but it's the same idea. Let's see, is this a valid argument? And so I went ahead and filled in all the T's and F's, so everything's plugged in here. If you want, you could even color code things differently. Like if you wanted all the T's to be blue and all the F's to be red, you could do that. You could even do that when you're writing it down as well. But I'm not going to do that. But I have my reference chart over here. Here are all my constituents. This is as big as a table as I'm going to give you on Quiz 9 and Quiz 10. Okay, 4 variables. That means there's only a possibility of it being 16 rows, 4 columns. This is as big as it's going to get. In fact, if you have one like this, you can basically just copy this over. Just be consistent in what letters you applied on. Like I'm using this all on K here. I could flip the letters around, and as long as I was consistent and where I apply them, it doesn't matter what letter gets what, as long as I consistently apply it throughout. So let's do these one at a time. Okay, so keep in mind, this is a premise. This is premise 1. This is premise 2. This is premise 3. This is premise 4, and this is the conclusion. Now look, the second premise here and the conclusion are actually quite simple. So what I'm going to do for each of these is I'm literally going to copy this stuff over. So for the n here, bam, because it literally, these are the values for n, and the conclusion is just n. So this is going to be it right here. Same thing with the second premise. The second premise is just n. So I'm just going to, this is where using technology makes this a lot easier. Bam. Those are all the values for m. Now these other 3 I have to figure out. So they're all arrows though, which makes this super easy. Because there's the rule for arrow, remember, is this. When you have, the only time an arrow does not work is you got a true left and a false right. So I'm actually going to be looking at these 2 columns in order to make this happen. So I'm looking at K and L, and I want to look and see if it's got, the only time where I can put an F here underneath this is if it's a true left and a false right. Like this one, look, true left, false right. That doesn't work. All the other ones are going to work. So that's what I'm going to do here. So I'm going to take a look at these column by columns. I'm just looking at the K and the L. So that's a good, yep, nope, and none of the other ones, but they all begin with F, so there's no way it could be a true left and a false right. So all these other ones are good. Now if I wanted to, I could also, I could copy the K underneath this as well, and I could copy the L underneath, if you don't want to refer back. I think this is the shorthand way of doing it. I think this is perfectly legitimate. All right, L arrow N, same thing. Now this time what I'm going to do, I'm looking at this column for the left side, and I'm looking at this column for the right side for this arrow, L arrow N. So this is my left side, and this is my right, okay, for this. All right, see, left side is L, so it's all these values. Right side is N, so it's those values. So that's what I'm looking at when I do this next one. So I'm literally looking at this and this, L and N. So it's an arrow as well, though, so same scenario. That one's a true. That's that one's going to work. This one's going to be a no. Okay, true, left, false, right. That's good. That's a no. That's good. That's good. That's good. That's good. That's good. That's a no. That's good. That's a no. And all the rest are good. They all start with F. There's no way it could be. If it starts with F, there's no way it could have a true left and a false right because they're all false lefts. All right. Last one here. M arrow K. So my left side is going to be this column, the M's, and my right side is going to be the K's here. Now, all right. So this is where using the reference sheet can be a little bit confusing, but if you know what if you know what you're doing, it's still pretty easy. So this here, this M, I put it in red. This is the left side, and the K here is the right side for this arrow. So what I'm going to do is I'm going to look at this. Like, for example, this would be my left. This is my right. That would be good. Left, right, good. So let me find one that's bad. So we can say, so this one right here, true left and false right. Well, how could that be a true left, false right? The F is on the left because this is what's actually going on. Okay? So let me get rid of some of the highlighting colors there so everything looks tiny. So that's what I'm referring to. My M here is my left side, and my K here is my right for this arrow. So that's what I'm referring to as I go through this. So this one's good, that one's good, 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 good. Like I said, no, no, good, good, no, no, good, good. All right. All the premises are done. So for right now, I don't care about any of this. Okay, so in fact, I'm going to, not all the constituent, that's not helpful. But all the constituent components, I don't need to worry about any of this stuff right now. All I'm worried about now are my premises, and I have 4. 1, 2, 3, 4. Okay, this is my conclusion over here. That's a separate thing I'm going to worry about in a moment. Okay, so what I want to look for is for the premises, 1, 2, 3, 4, where do I have all T's? Right there, and I'm going to go ahead and highlight those rows, or make, there we go, let's make the, we'll highlight it in red just so we can see it. So these are the rows that matter. So it's got an F in it, I don't even care, even just one F, nope. Nope, 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 nope. Oh, almost, there's an F there. Nope, nope, nope. Ah, there's an F. Ah, F. Nope, there is only one row where it's all T's. Okay, only one row where it's all T's. So what I'm gonna look for, this is really the only row in the whole thing now that matters. And what we want to see over here is what is the conclusion. If the conclusion is also true, ding ding ding, which it is. Let's not do all that. All right, so if the conclusion is also true, which I said it is, this means that this argument is valid. Now, for some reason in this row it was false here, that would mean that the argument was invalid. We know that this would be the counterexample. But yeah, the argument is valid. Let's now test it in the tree just to make sure. We should also get that it's valid, which means everything that we break down should close. Let's do that. And so for the tree method, I went ahead and stacked our premises here, and including our conclusion. Remember, after you stack them in the tree, the first thing you actually do in the tree is you negate the conclusion. Alright, so that's done. That's the first thing. Next thing we do is we're going to go up the tree, seeing are there any rules that stack? None of them stack. Again, this thing doesn't, the M doesn't break down anymore. It's good. But all 3 of these are splits. So I like to start at the top, right, and work my way down. So I'm going to split this one. The rule for arrows in a tree is it splits, and you negate the left side, and you keep the right side as is. Again, you're basically doing the rule of material implication on it. Okay, so anything here, any contradictions in this stream? No. Any contradictions in this stream? No. Moving on. We're going to break down this L arrow N now. Now this one, it's going to flow downstream into both this one, and it's going to flow downstream into this one. So we're going to have to attach it to this because it's flowing out of this. These are both open. They're both leaking right now. They haven't closed off. So this is going to break down here and here because it's flowing down into this and it's flowing down to that. So it's an arrow. The rule for arrows is you negate the left, keep the right as is, as a split. So we're going to split here and do that. Squiggle L. We keep N as is. And it's also flowing down to this one. Squiggle L, N as is. So look here. This one's now broken down. Take a look. Does this one stop up? Nope, this one's still leaking. This one stop up? Yes. The N and the squiggle N negate each other. So this one's no longer leaking. Look at this. This now. This one closes up, squiggle L, and L means this one's done. This one's not leaking. And the squiggle N and the N mean this one's not leaking. So these 3 that we made 4, these 3 have already shut off because there are contradictions in them. So the only place where it's still flowing is right here. So when we break this next thing down, we don't need to add it onto these things because these things are done flowing. If you think of it, the breaches have been sealed. Here, we still need to break this down, and it's only going to flow out into this. Let's see what happens. It's also an arrow, M arrow K. So what the arrow does is it splits, and we get squiggle M, and we get K. Let's take a look. Squiggle M. Do we have a? At first, you might think, oh no, we don't. There's no opposite squiggle. There's no opposite. Yeah, way up here in the M. That's way up here still in the trunk of this tree, so to speak. But if that makes this, these are opposites, this closes off, the leak stops. And what about this one? K, squiggle K, flows down here. So look, every single place, if you will, every single valve, every single tributary, or every branch, depending on what metaphor you want to think about this as, closes. And when everything closes, that means that the argument is valid. It's valid when there are, if you want to think about these, I like to think of these as valves or faucets or spigots. No leaks. No counterexample. You could think of counterexample. That's the one that's going to leak. That's the branch that's going to rot. Again, choose your metaphor. Okay, well, let's take a look at another one for practice. All right, now we're going to do a table for basically the rule of distribution. Actually, in this direction, we're factoring the A out, but it's nevertheless the law of distributivity. Let's prove that it works. Not with a proof, but with a table. Let's prove that it's a valid argument. All right, just because. So I've got our constituent components there. What I'm going to do is I'm just going to use these as references. I'm not going to copy literally A, B, C over every time we see it, because I think that ends up taking more time. So this is basically how to use the table with its constituents to your advantage. So first thing I'm going to do, remember we want to work ourselves to the main operator. So in the premise, this is premise 1, and there's only one premise in this argument. This is our main operator. And in the conclusion, this is our main operator, the thing not in parentheses. So this is both of these are the final column we want to get to. But in order to get to this, to get the values for this, we have to say this from the left and the right. In order to do the left and the right, we have to get this value, this dot, we have to get this dot, and then for the conclusion, we have to get this XOR in order to figure out how does it relate to the left side. So you're basically comparing the left and right sides in each of these main operators to figure out what's going on. That means first we have to figure out what the operator is in these components. So for example, for this left side here, A and B, the rule is AND. And so the AND rule for tables is the only time an AND works is when you have all T's. So it's A and B that we're looking at. So I'm going to look over at these A and B. So the only time this is going to work is when I've got all T's. And I'm just looking at it. Those first two rows, that's it. Look, T's on A's and B. Everything else is some kind of combo. So I'm just going to jot that down. Yep, this works. Yep, this works. No to the other 6. Okay. Left side is done. So in order to get this XOR, I'm halfway there. I also need to compare A and C for this dot. So I'm looking at this column and this column to figure out A and C. So I see, yep, there's one all T combo. Let's put that. So this is a no. There's another all T combo, and all the rest are one or the other. Like, oh, you got a T and an F, you got an F and a T. So that doesn't work. All the other ones would be Fs. Okay. And then that means we've got the left side for the premise, we've got the right side for the premise. That helps us figure out the XOR. Now the rule for XOR is this. Either one is true and the other is not. All right, so you have to basically put it this way. You need one T, one F. Any other, you got all T's? Nope. You got all F's? Nope. One has, you got to have one T, one F. That's the rule for this. So that's what we're going to look at. So like for example, this first row here, both T's? Nope. One T, one F? That works. Look, one F, one T? That works. F and F? No. 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 You can never have a match. It has to be a mix and match. So for XORs. So there you go. That is, this right here is the set of possible values for the premise, this. Okay, now we got to figure this one out. Okay, so to get to this AND, the left side is going to be it's going to be this stuff, the 4 T's, 4 F's. I'm not going to copy and paste that over. I could, because it's far away here. You might think, oh, that's a lot, that's pretty far to look back on. But I'm not going to copy it over, although you could, just because I'm going to try and make this as streamlined as possible. But I am going to do this one, B XOR C. So I'm actually going to be comparing these two columns here to figure out the XOR values. And we just did an XOR. The way XORs work is you can never have a match. So like here, all T's, nope. Mix and match, yep, yep, nope, nope, yep, yep, yep. So let's do that again. So yeah, all T's, not going to work. T and F, yeah. F and T, yep. F and F, nope. T and T, No. T and F? Yeah. F and T? Sure. F and F? No. Alright, so now these are the values for the right side of this. Now the left side values are here, this A. And I said I wasn't going to do it, but for the sake of just making it, we're looking right here, not having to look completely across, all the way across the screen, I'll go ahead and copy those A values over. So it's just A, so it's going to be exactly what we saw way over on the left side, nothing new here. I'm just copying the A values here. But what we're trying to determine is this AND. And the way an AND works is you got all T's is the only time it works. You got to have T between both the left and right side. It need to be both T's. That's the only time you get a T for the whole thing. Any other combination, you get a T and F? Nope. F and a T? Nope. F and an F? Nope. Only all T's. So no. Yep. Yep. No. 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 So here you go. Here are the values for this premise. Now here's how we know we have a rule of substitution here. Look at the premise. So let's do this first of all like a normal table. Look, so look at the premise. Whenever all the premise has T's, the conclusion, look, it also has T's. So what does that tell us? First of all, that the argument is valid. Okay, that's the first thing. So that's neat. That's what we're looking for, really. But I also want to say here that you have a rule of substitution. The way we know a rule of substitution works, and I've said this before, is when, look, the values of the premise, the whole set, matches the value of the conclusion exactly. Like, if I took the conclusion here and put this as a premise, we would get the exact same thing. The argument would be valid in both directions. Okay, because the value for the premise and the value for the conclusion are identical. That's why rules of substitution work, like De Morgan's law, or distribution, or commutativity, or associativity, or any of those that are rules of substitution. The rules of inference or the rules of derivation are different. But for the rules of substitution, this is exactly what's happening. You know you can switch between them because their truth values are exactly identical. Not similar, identical. Look, F, 2 T's, F's. F, 2 T's, F's. The values are identical. So that's why we could flip this around. Okay, I'm not even going to do the table in the opposite direction because it's the same. It's literally the same thing. I am going to do the 2 trees though, because we want to see. Well, in order to figure out this truth via the tree method, we'd have to do it both ways. So that's what we're going to do, and we're going to see what that gets us. So I went ahead and set up for the tree the exact problem we were just doing: A and B XOR A and C, A and B XOR C. So remember, the first thing that we do for a tree is we negate our conclusion. Okay. Then the next thing we're going to do is see, do we have any stack rules, any split rules, and then any split and stack rules. So do I have any stack rules? No. Do I have any split rules? Yes, I have a NAND. Okay, that's a not AND, which means this is the same thing. A not AND is the same thing as saying neither this nor that. So it's going to split, and both sides get squiggles. So it's the opposite of each side. So we get squiggle A on the left, and then we get squiggle B, X, or C on the right side. So this one breaks down that way. All right. Now what I'm going to do is I have a choice. I can go ahead and break this down and let this flow into both these parts. I can do that. I'm actually going to break this down first. Now, the way that the downstream things work is, since I'm breaking this down, it's only going to flow downstream from here. It's not going to vomit back upstream and go into this. Okay, this is its own thing now. This is its own thing. Only things that flow from up here flow downstream into each tributary. So let's break this down, and it's going to break down here, this way. It's not going to go back up again. That's the thing that I want to point out. So it's an XOR, that's a split and stack. So the way, it's an XNOR. The way XNORs work is you split and stack, and basically you say one side is exactly as it is, and the other side is not that. Because that's what you're saying in an XNOR. It's basically the same thing as double arrow. It's either all or nothing. That's what an XNOR is saying. So cool. That's broken down. Any contradictions, though? No. Alright, so now we're going to break down this thing. It's an XOR. Not an XNOR, but an XOR. And it's going to be plopping down in 3 places. It's going to flow down into, it's going to flow downstream into this, it's going to flow downstream into this and this. And let's see what we get. Once you get it right in one spot, you just put the same thing in the others. So you're going to, the way XORs work, or you say, you get a split and stack. One stack is going to be, you're going to say yes to the left side, no to the right side. And then the other stack is going to be no to the left side, yes to the right side. So what do I mean by that? So split and stack for XOR. You say yes to the left side, and you say no to the right side. And then you say no to the left side, and yes to the right side. I don't even need that parentheses there. Alright, there it is. Same thing is going to flow down into this one. I don't even have to change anything, so really I'm copying and pasting. What's flowing downstream here is infecting, if you will, everything. And here I'm going to scoot this just a little bit, split and stacking, but I'm doing it this way. Distorting the line just a little bit for the sake of space. Whew. Alright. So now I can say that's broken down. So this looks messy, but it's actually pretty simple. So let's watch this. So first of all, we've got basically 6 places where we need to break things down. We've got this is something still flowing, this is still leaking, this is still leaking, this is still leaking, this is still leaking, this is still leaking. But I think you'll see it goes relatively quickly. Take a look at this. Let's start with this one. Let's break this simple stack. Let's break that down. Look, we get A and B. Look, bam, that closes immediately. Look, the A and the squiggle A don't work, so that one closes. This one here, look and see, do I have a stacked one first? Yep, I got A and C, and look A, not A, that one closes down. Okay, I'm going to come over to these two because they do the exact same thing that one did. Look for the stack rule. A, B, look, B, not B, that one closes. Same thing here. A, C, that is the stack rule. Do the stack one first. Squiggle C, C, that one closes. Here's where things get a little messy. So if I do the stack rule for each one, so if I break this down, I get A, B. I break that one down, I do A, C. I don't have any contradictions yet. It's starting to make me nervous. I'm having to write real tiny. But look, this is a split rule. So is this one, so we get, look, squiggle A here, squiggle C here, because it's a NAND. And look, there we go. The squiggle A here doesn't go with that A, so I'm going to end up putting the little block symbol here. This squiggle A does not go with this A. This squiggle C does not go with this C here, so everything closes here. The same thing happens here. When I get squiggle A and squiggle C out of this, the squiggle A and this A doesn't work. Squiggle C, and there's actually 2 C's in here. No, doesn't work. Everything closes, so that means the argument is valid. Start writing tiny here because I ran out of board space. But let's take a look at it the other way. And this time I'm going to try and give myself a little bit more board space so I don't have to write tiny towards the bottom. But we're going to do the argument in the opposite direction just to show that the rule works both ways. So we just proven you can go from this to this, again, minus the negation, because the negation is something we did in the tree. Let's see how it looks in the opposite direction to prove that the rule works, because that's what you have to do in a tree. In order to prove a rule in a tree, you have to do both trees. This is actually where the table has the advantage and you do less work. If you can prove that the truth sets for the premise and the conclusion actually have the exact same truth values, you know that the rule's there that way. But for a tree, you actually have to do both trees. So there, the table actually has the advantage. So again, pros and cons for each. I think in the long run, the tree has far more advantages than the table, especially as the problems get bigger and more sophisticated. But let's take a look at the rule, same one, in the opposite direction. Alright, we've got the tree set up in the opposite direction. Let's go ahead and start it. So first of all, we need to negate the conclusion. There we go. And the first thing we want to look for, remember, we want to look for rules that stack, rules that split, and rules that split and stack. So we actually have a stack one right here. Just have a plain old AND. So that's going to stack. We get A and B XOR C. So that one breaks down like that. And then let's go ahead and see what breaks down from here. So we have an XOR here, this B XOR C. The way that this one's going to break down is going to be like this. It's a split and stack, so I'm going to go ahead and do it. And what I get here with a split and stack is I get, this, or this, or this, or this. So a positive and a negative, negative and a positive. Okay, so this one's broken down. Now next I have an XNOR. And the XNOR is going to flow downstream in both these directions. It's going to flow here and it's going to flow here. And the way this one works, it's going to split here into both. And it's going to stack into both. And the way that an XNOR works is basically on the left side you get everything as it is, and the right side you get as it's not. So what that means for the XNOR is on the left side of each of these split and stacks, I'm going to get A and B, and A and C. On the left side of each split and stack. And on the right side of each split and stack, I'm going to get those, not those. So squiggle A and B, squiggle A and C, and also squiggle A and B, squiggle A and C. So this one's not broken down. So now everything has flown downstream. So now each one of these four tributaries or spigots is its own thing. Everything's only going to flow downstream from here. So let's start with this one. First of all, let's break down this. A and B. Nothing's happening yet, but I broke it down. Let's do this one now. A and C. Broke it down. This one shuts down because C and not C. Okay? So these stack ones, I got that out of the way first. These are going to be splits here. These are going to be splits here. So I'm going to do these stacks next. Same thing. Let's do the A and B. It's A and B. And I can stop right there. I don't even have to do anything else because I've already got the B and the not B. Those don't work. So these two close. So now I'm only dealing with these. So first of all, let's break this one down. It's going to be a split, and it's a NAND. And the way NANDs work is they split, and you basically are doing material implication. So you're saying, when you got a NAND, you split it, and you say, not the left side, not the right side. And this can stop right here. Look, squiggle A and A. So this one stops. Squiggle B and B. This one stops. So this one, 1, 2, 3, 4, these are all good. They all close. Let's take a look at this one. Let's start with the first one here. It's going to be the same split we just did a moment ago because it's also a NAND of A and B. So A NAND B, I suppose I could say. So it's going to split, and I'm going to get squiggle A and squiggle B. This one stops immediately. A and squiggle A, those don't work. This one though, no contradictions yet. Look, this squiggle B here, there's not a contradiction. So I need to break this one down too. And it's going to flow only downstream into this one because this one's already shut off. So what does that break down into? We get this. It's a NAND, which means it's going to split, and we're going to get not of the left and not the right. So we get squiggle A and squiggle C. And look at this one. A, squiggle A. That doesn't work. So it stops. This one's not leaking. And this one, not C and C. That one. So everything's been broken down. And we're done. Everything closes, which means that the argument is valid. And since for the tree it works in both directions, we know that the rule is going to work. So now that we've done a lot of practice, what I want to do is I want to take a look at just a couple of problems from Quiz 9 and Quiz 10 to get you started. Alright, here's the first of 3 problems that are actually on Quizzes 9 and 10. I'm going to do it both the table way, that would be what you do on Quiz 9, and the tree way that you do it on Quiz 10. So for this one, we got 2 variables, x and z. Not too much going on here. TT, FF, TF, TF. Alright, now let's look at the actual premises. X arrow Z, premise 1. Just squiggle Z, premise 2. And our conclusion is X. Okay, so premise 1, premise 2, and our conclusion is X. So let's determine these values. X is going to be really simple. We're just going to copy over what X is. There's nothing more sophisticated than that. Now to get X arrow Z, we're going to use the arrow rule. The arrow rule says you get a true left and a false right. That's the only time an arrow doesn't work. So this one works. Nope. Yep, yep. And then this is squiggle Z. It's going to be whatever the opposite of Z is. So since Z is TF, squiggle Z is going to be FT. And then what we look and see is, for our premises, we got two premises, premise 1 and premise 2. Is there an occasion where all the premises are true? Yep. There they are. Row number 4. What's the conclusion? It's false. What does that tell us? This argument is invalid. And in that scenario, X is false, and so is Z. So we can also say X equals F, Z equals F. Okay, if we do the tree, we should get the exact same thing. So let's do it. X arrow Z, squiggle Z, X, and then we negate our conclusion, the X. So both of these are broken down. We don't have to do anything else. They can't be simplified further. So the one thing we have to do is this arrow here, and the way the arrow rule works is it splits, and it says you negate the left side, and you keep the right side as is. And everything's broken down now. Anything here? Nope, no contradictions. Anything here? Yeah, we got one. So this open branch, look, every time we've got it, what is X every time we see it? It's squiggle X. What is Z every time we see it? It's squiggle Z. And there you go. The argument is also invalid through the tree method, and we get the exact same thing. Squiggle X and squiggle Z. That's this one on quiz 9. This is the quiz 9 version. This is the quiz 10 version right here. Let's take a look at another one from quiz 9 and quiz 10. Alright, here's another one from quiz 9 and quiz 10. We've got squiggle O, double arrow, squiggle L, get O and L. Is it valid or not? Well, let's see. Our constituent components are O and L, just two. So that's going to be TT, FF, TF, TF. Let's write our variables in there. Squiggle O, double arrow, squiggle L. And we're going after O and L. Okay, to get our, so we got only one premise here, and then our conclusion. Let's start with the premise. To get squiggle O, it's going to be the opposite values of O. F, F, T, T, and to get squiggle L, it's going to be the opposite values of L. F, T, F, T. And the way a double arrow works is it's all or nothing. So when you got all matches, all Fs, it works. Any kind of combination, no, no. There we go. All or nothing. So here we go. Here's the values for this premise. Okay, so for O and L, to get these values, we look at O and L, and the only time an AND works, because that's the main operator here, is when we've got all T's. So there we go. Got all T in the first line, and then the other ones are going to be nope, nope, nope. So these are the values for the conclusion. Alright, so let's take a look. Premise, true. Conclusion, true. Looking good so far, but we've got premise, true, conclusion, false. So what does that mean? The argument is invalid. And we also know when it's invalid in this scenario, when O is false and when L is false. Okay, the other way to put that, when O equals F and when L equals F. Right, let's do it the tree method and see what we get. So we get squiggle O, double arrow, squiggle L, and we get O dot L. First thing we do in the tree is we negate the conclusion. That gives us a NAND. So the double arrow is going to be a split and stack, but this NAND is going to be a split. We don't have any stacks that we can do, so we get this. Squiggle O, squiggle L, that's the rule for NAND. Basically, it's like we're doing De Morgan's law on it. If we had a this, it would, De Morgan's law, turn into this. It would split into this. So this is broken down. And then the way that a double arrow works is this. On the left side, you get things as they are. And on the right side, you get them as they are not. And so that's going to flow downstream into both. And let's see what we get. Any opposites here? No. Opposites here? Yep. Opposites here? No. Opposites here? Yep. So there are two open, flowing spigots, and in both cases we get the exact same thing. What is O every time we see it? Squiggle O. There it is. There it is. No contradictions. And squiggle L. Same thing in this one. Squiggle O. Squiggle L every time we see it. So it's invalid, and there's the counterexample, which is exactly what we got in the table as well. It matches. So this is the Quiz 9 version. This is the Quiz 10 version. Let's take a look at another one from Quiz 9 and Quiz 10. All right, let's take a look at one more from Quiz 9 and Quiz 10. This is the Quiz 9 version. We've got squiggle S, arrow T, squiggle S, double arrow, squiggle T, and we're solving for S, ultimately. I already put the true, false values in here. Only two variables, so this one's pretty straightforward. So let's do this. I'm going to do some copying and pasting for this one just to make sure it's clear. So for the values for squiggle S, we've got F, F, T, T, the opposite of whatever S is. T is going to stay the same. I'm going to copy and paste it over here. Now we've got our arrow rule. Our arrow rule says true left and false right is the only time it doesn't work. All the other ones are good. So here we go. This is the only values for the first premise. Let's do the second premise. Now the main operator here is actually the negation. It's a double narrow. It's saying not this. So for S, let's copy it over just for the sake of making this easy. And for squiggle T, I'm going to just do the opposite of T. It's going to be FT, FT. And the way a double arrow works is all or nothing. So nope, yep, yep, nope. But then it's negation of that, so it's going to be T, F, F, T. So here is the second premise. And then for S, I'm just going to copy that over as is, T, T, F, F. So here we go. Let's look at our premises when we got all T's. First row is good. That's it. First row. That's the only time where we got true premises. What's our conclusion? True. What does that tell us about the argument? It is valid. Argument is valid. Let's look at it, the tree method, to confirm that it is indeed valid. Let's do this one. First thing we want to do, I've got everything stacked here. First thing we're going to do is negate the conclusion. And then if we have a stack rule, we'll use that. Do we have a stack rule? No. Do we have a split rule? Yes. The arrow rule says this. Because this one's already broken down, we can't break it down anymore. The arrow rule says we take the arrow and we take the left side and we negate it. So it'd be S, and we keep the right as it is. So already here, this S and squiggle S, they break down. So this one works. So we got, this is the only thing that we're going to flow into here is this. And we have this right here, and this one's tricky. We have a double narrow. So a double narrow is a split and stack rule, and it's basically the same thing as an XOR. So what we do is this in an XOR. For the left side, you keep it as it is, and the left split stack, you keep the left side as it is, and then you have the opposite or contrary of the conclusion. What's the contrary of squiggle T? T. And then what you do is you take the opposite of the left side and you stick that in, and then you keep the right side as it is. Okay, so that's broken down. So this is the way you break this one down. Now let's take a look here. Opposites in this, yeah, S and squiggle S. Okay, so S and squiggle S, and then here we got T and squiggle T. Everything that breaks down everything stops. That means the argument is valid. As the table got us, we get it in the tree as well. So that's it on these couple of sample problems from quiz 9 and quiz 10. Okay, so quiz 9 and quiz 10, 13 problems total, 130 points out of 100, just like many of the other quizzes. So if you have other questions, email me at thomasb@usca.edu.